Good morning, students. Myself, Karthikkumar, Department of ECE, as working as an assistant professor from Erode Sengunthar Engineering College, Tamil Nadu. So, in this video belongs to AICTE PRERANA scheme for preparing SC students for higher education regarding GATE examinations. So, in this, today the session belongs to analog circuits, so which is a major topic in GATE syllabus. Analog circuits. In these analog circuits, today in this session, we are going to see about the operational amplifiers, that is operational amplifier and its configurations, then function generators, wave shaping circuits, triple five timers, and voltage reference circuits. Okay, so in this session, we are going to see the some practiced problems which is already occurred in gate examinations and what are the applications of those circuits. Okay, so operation amplifier configurations, function generators, wave shaping circuits, and triple five timers. Okay, so first of all, we just take the case. So these circuits belongs to linear integrated circuits, simply called. Okay, so what is mean by linear integrated circuits? So linear integrated circuits is nothing but the circuits which obeys the linearity property. Okay, so in this case, the Ohm's law. Okay, the circuit whichever obeys Ohm's law is called linear circuits. Okay, that is whenever we are changing the input parameter, the output parameter also changes linearly. So this is called a linearity property. So circuits which obeys the linearity property, that is Ohm's law, is called linear integrated circuits. Okay, so if we say in deep manner, the voltage and current at specified points in the circuits of analog chips vary continuously over time. In contrast, digital chips only use and create voltages or currents at discrete levels with no intermediate values. In addition to transistors, analog chips often include a large number of passive elements. So, what are the passive elements? Capacitors, resistors, and inductors. Okay, so the chips often include a large number of passive elements than digital chips. Inductors tend to be avoided because of their large size, and transistors and capacitors together can do the work of inductors. So, in this, analog chips may also contain digital logic elements to replace some analog functions or to allow the chip to communicate with the microprocessor. For this reason, and since logic is commonly implemented using CMOS technology, these chips use BiCMOS process by companies such as Freescale, Texas Instruments, ST Microelectronics, and others. Okay, so yeah, analog chips may also contain digital logic elements to replace some analog functions or to allow the chip to communicate with the microprocessor. So for this reason only, the logic is commonly implemented using CMOS technology. These chips use BiCMOS process by companies such as Freescale, Texas Instruments, ST Microelectronics, and others. This is known as mixed signal processing and allows a designer to incorporate more functions in chip. Some of the benefits include load protection, reduced parts count, and higher reliability. Okay, so pure analog chip is information processing have been mostly replaced with digital chips. I am repeat once again. So pure analog chips in information processing have been mostly replaced with digital chips. So analog chips are still required for wideband signals, high power applications, and transducer interfaces. So the research and industry in the field continues to grow and prosper. Some examples of long-lived and well-known analog chips are 741 operational amplifier and triple five timer IC. Okay, so that's why these things belongs to analog circuits and it is a major part in gate examinations. So today we are going to see these topics in this session. Okay, so the power supply chips are also considered to be analog chips. Okay, I am repeating once again, power supply chips are also considered to be analog chips. Their main purpose is to produce a well regulated output voltage supply for other chips in the system. Since all the electronic systems require electrical power, power supply ICs are important elements of those systems. Okay, so the important building blocks, that is the basic building blocks of analog chip design, that includes current source, current mirror, differential amplifier, voltage reference, band gap voltage reference. Okay, so these are all the basic building blocks of analog chip design. Okay, so that is current source, current mirror, differential amplifier, voltage reference. Okay, so today we are going to see about the analog circuits, that is operational amplifier, its configuration, function generators, wave shaping circuits, and voltage reference circuits. Okay, so in this session we are going to see about the basic, that is what is mean by function generator, what is mean by wave shaping and those things, and we are going to solve few problems which will be frequently asked in gate examinations. Okay, so before that we will see the basic description about the circuit. Okay, so first what is maybe analog circuit? So the analog electronics or analog circuits are a electronic system with continuously variable signal, in contrast to digital electronics where signals usually take only two levels. The term analog describes the proportional relationship between a signal and a voltage or current that represents the signal. Okay, so first of all we have a doubt. Okay, so what is mean by analog and what is mean by digital? Okay, so before going to the topic we will discuss about the analog versus digital circuits. Okay, so analog circuits and digital circuits is a classical way, okay, classical way of differentiating the two types. Okay, two types of electronic circuits based on the signal. So based on the signal they process. Okay, the analog circuits and the digital circuits is a classic way of differentiating between two types. Okay, between two types of electronic circuits based on the signals they process. Okay, to put it in simple words, analog circuits deal with continuous analog signals, whereas digital circuit deals with discrete digital signals. Okay, so from this slide you will get a clear idea about what is analog and what is digital. Okay, in depth we will see some comparisons between those things. Okay, so first, analog circuit. So analog circuits operate on continuously variable signals, also known as analog signals. Okay, in a continuous manner. But in digital circuits operate on discrete variable signals. Okay, discrete variable signals are digital signals. Okay, so this is a digital circuits. So that is the signal exists only in two levels, 0 and 1. Okay, binary digital signaling. In analog circuits, depending on the efficiency and precision, it is quite difficult to design analog circuits. Okay, depending the efficiency and precision, it is quite difficult to design analog circuits. But in digital circuits are relatively easy to design with many automated tools available for various stages of design and analysis. Okay, so digital circuits are relatively easy and with many automated tools. Okay, with many automated tools, digital circuits are relatively easy. Okay, so next one, when interacting with the physical, okay, when interacting with the physical world, analog circuits can directly accept the signals from outside as the data is already analog. Okay, so we are receiving analog, this device will easily accept the physical parameters. Okay, but in digital, if a digital circuit has to acquire data from physical world, the analog signals must be converted to digital signals first. Okay, so analog signals must be converted to digital signals first. So as there is no need for data conversion, there is ideally no loss of information. Okay, so whenever we are converting, or whenever we are giving some inputs, if the input is directly processed, then there will be no loss. If we are converting from one term to, that is one parameter to another parameter, one form to another form, the signals might get lost. Okay, so that problem will be rectified in analog circuits. But in digital, during the process of converting analog signals to digital signals, there might a significant amount of data loss, which can result in loss of information. Okay, so the during the process of converting analog signals to digital signals, there might a significant amount of data loss, which can result in loss of information. Okay, so this one is a major difference between the analog and digital circuits. Okay, if precision and accuracy are not a criterion, then analog circuits can be simple and inexpensive. Okay, so each and every electronic devices, the precision and accuracy is a much needed parameter. Okay, so if precision and accuracy are not a criterion, then analog circuits can be simple and inexpensive. Okay, so but in a digital, even with the simple design techniques, okay, simple techniques, the at a low cost, the digital circuits can provide good accuracy and precision. Okay, so these are the major things. So let us see there are some of the applications of analog circuits. Okay, analog integrated circuits were primarily designed using hand calculations and process kit parts before the invention of microprocessors and other software dependent design tools. Okay, analog integrated circuit design is used for designing operational amplifiers, linear regulators, oscillators, active filters, and phase locked loops. Okay, the semiconductor parameters such as power dissipation, gain, and resistance are more concerned in the designing of analog integrated circuit. Okay, and most of the thing that is the analog integrated circuit design is used for designing operation amplifiers, linear regulators, oscillators, active filters, and phase lock loops. Okay, so the main parameters such as in the semiconductor parameters such as power dissipation, gain, and resistance are also concerned during the designing of analog integrated circuits. Okay, so in this session, we are going to see about those analog circuits. Okay, we already said that operation amplifier, wave shaping circuits, then voltage reference circuits, then function generators. Okay, so these circuits have been discussed today for our gate examination. Okay, by some solved problems also. Okay, So first of all, see the things. Okay, what are the those things? So exact definitions. Okay, the exact definition and application. So based on that, we will get a clear idea about those circuits to solve some problems based on our formulas and techniques we used for designing. Okay, okay. First of all, operation amplifier. So the operational amplifier, or an op amp for short, is fundamentally a voltage amplifying device designed to be used with the external feedback components such as resistors and capacitors between its output and input terminals. Okay, so it is a voltage amplifying device designed to use with the external feedback components such as resistors and capacitors between its output and input terminals. Okay, so in depth we can say the operation amplifier as is a DC coupled high gain electronic voltage amplifier with differential input. Okay, with a differential input and usually a single ended output. Okay, so the things which I said we can see in this picture. Okay, so I will tell you the what are the configurations. Okay, but first of all we will discuss first we will detailed about the device, or that is operation amplifier. What is the operation amplifier? Okay, so the operation amplifier is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single ended output. In this configuration, an op amp produces an output potential that is typically 1 lakh times larger than the potential difference between its input terminals. Okay, can you get this? So I will once again repeat. In single ended output, that is, an op amp produces an output potential relative to circuit ground. Okay, that is typically 1 lakh times larger than the potential difference between its input terminals. Now we can exactly predict, that is a clear idea about the linearity property. Okay, so now operational amplifiers had their origins in analog computers, where they were used to perform mathematical operations in linear, non-linear, and frequency dependent circuits. Okay, so later on we will see about what are the non-linear and frequency dependent circuits. Okay, first in this session we will see about those devices which I mentioned. Okay, so the popularity of an op amp as a building block in analog circuits is due to the versatility. Okay, by using negative feedback, the characteristics of an op amp circuit, its gain, input and output impedance, bandwidth, etc., are determined by external components and have little dependence on temperature coefficients or engineering tolerance in the op amp itself. Okay, once again I repeat, by using negative feedback, the characteristics of an op amp circuit, its gain, input and output impedance, bandwidth, etc., are determined by external components and have little dependence on temperature coefficients or engineering tolerance in the op amp itself. Okay, so now the op amps are widely used in electronic devices today, including vast area array of consumer. Okay, in consumer electronics, LIC chips have been replaced now. So it is a vast array of consumer, industrial and scientific devices. Okay, many standard IC op amps cost only a few cents. Okay, that is the ICs are very much cheap. Okay, it's a non expensive. So in this sense, for which are using for consumer, industrial, scientific devices. Okay, so however, some integrated or hybrid operation amplifiers with special performance specifications, okay, that may little expensive when compared to some already discussed. Okay, so some special performance specifications may cost over. So that is in a small quantities. Okay, so op amps may be packages or components are used as elements of more complex integrated circuits. Okay, packaged as components are used as elements of more complex integrated circuits. Okay, the op amp is one type of a differential amplifier also. Okay, so this is a one type of differential amplifier. Other type of differential amplifier includes fully differential amplifier, instrumentation amplifier, the isolation amplifier, which will be discussed later further on. Okay, so that's not a problem. So some fully differential amplifier, instrumentation amplifier, uh, isolation amplifier, instrumentation amplifier, but with tolerance to common mode voltages that would destroy an ordinary op amp. Okay, a negative feedback amplifier. Okay, so differential amplifier, instrumentation amplifier, the isolation amplifier, common mode voltages, that is with the tolerance to common mode voltages. Okay, so the negative feedback amplifier also belongs to those kind. Okay, so let us see the operation amplifier configuration. So we are going to write the gate examinations in the sense of those configurations and related problems only. Okay, so there are two basic op amp configurations in wide use. They are inverting amplifier and a non-inverting amplifier. Okay, so these are the operation amplifier circuits. Okay, these configurations form the basics for many other related applications. So one is inverting amplifier, other is non-inverting amplifier. Okay, so in the inverting amplifier, the input is given in the negative terminal. Okay, and positive terminal is grounded through a resistor. Okay, in non-inverting terminal, the exact opposite. Okay, so the positive is given to an input and negative is grounded with some feedback across the input and output regarding a ground. Okay, with respect to ground. Okay, so this is the inverting operational amplifier and non-inverting operation amplifier. So the two configurations are used here in a general operational amplifier. Okay, so these are the basic things regarding a operational amplifier. Then applications of operational amplifier. So application amplifier, operation amplifiers, where are we are using those things. So it is used in wide variety of applications in electronics that we already know. Some of the more common applications are voltage follower, selective inversion circuit, a current to voltage converter, active rectifier, integrator, a whole wide variety of filters, and a voltage comparator. Okay, so these circuits are designed using an operational amplifier only. Okay, as a voltage follower, selective inversion circuit, a current to voltage converter, active rectifier, integrator, a whole wide variety of filters, and a voltage comparator. Okay, so these kind of circuits have been replaced by analog ICs nowadays, and we will see those circuits later. Okay, so let us go for next one, function generator. Okay, so what is a function generator? We already know that signal or function generator is a device that can produce various patterns of voltage at variety of frequencies and amplitudes. Okay, I repeat once again. Yeah, signal or function generator is a device that can produce various patterns of voltage at a variety of frequencies and amplitudes. A common use is to set the response of circuits to be a known input signal. Okay, a common use is to test the response of circuits to a known input signal. Okay, that's it. So most function generators allows you to generate sine wave, square wave, or triangular AC functional signals. Okay. So in this, for depth, we will say about some words about function generators. Function generators is usually yeah, test equipment only. Okay, test equipment or a software used to generate different types of electrical waveform over a wide range of frequencies. Okay, so some of the common frequencies produced by the function generators is sine wave, square wave, and sawtooth waves. Okay, sawtooth waves. So these waves can be either repetitive or single shot. Okay, single shot or a repetitive. Okay, so integrated circuits used to generate waveforms may be described in generator ICs. Okay, so we already are discussing about the analog circuits. So used to waveforms may also be described as function generator ICs. In addition to producing the sine waves, function generators may typically produce other repetitive waveforms. Okay, so other repetitive waveforms, so what are the waveforms? Includes a sawtooth and triangular waveforms. Okay, other than sine wave, we consider that a sawtooth and triangular waveforms, square wave also. Okay, another feature include on many function generators is the ability to add a DC offset. Okay, that is a common thing you already know. So although function generator covers both audio and RF radio frequencies also, okay, they are usually not suitable for applications that need to low distortion or stable frequency signals. When those traits are required, other signal generators would be more appropriate. Some function generators can be phase locked to an external signal source or another function generator. Okay, so the function generators are used in the development, test, and repair of electronic equipment. For example, they may be used as a signal source to test amplifier, or to introduce an error signal into a control loop. Okay, for example, I repeat once again, they may be used as a signal source to test amplifier, or to introduce an error signal into a control loop. Function generators are primarily used for working with analog circuits related to pulse generators, are primarily used for working with digital circuits. Okay, these are all the things about function generators. So next we see the what are the main applications of those function generators. Okay, so that function generators create clock signals to digital circuits, test communication circuits, generate signals to send to integrator or differentiation circuits to test their outputs. Okay, so send pulses to circuit to trigger events, vary pulse widths PWM to control a motor speed. Okay, so these are all the things which are mainly used as a function generator. Okay, so next circuit is wave shaping circuit. Yeah, right. Okay, so in this wave shaping circuit is used to perform any one of the following functions, that is to hold the waveform to a particular DC level, to limit the voltage level of the waveform of some presenting value, and suppressing all other voltage levels in excess of the present level. Okay, so can you understand? Okay, so this the wave shaping is used to perform any one of the following, that is to hold a particular DC level, to limit the voltage level of the waveforms, or suppressing all other voltage levels in excess of the present level. Okay, so the wave shaping circuit in electronics is the modification of shape of an electronic waveform. It is close connection with the waveform diversity and the waveform design, which are extensively studied in a signal processing. Okay, so we don't bother about much more about this waveform shaping. So waveform shaping, which is it is also close connection with the waveform diversity and waveform design. Okay, which are extensively studied in signal processing, shaping the waveforms or of a particular interest in active sensing. Okay, that is sensing means the radar and a sonar. So which is and that part digital signal processing, that is a signal processing is majorly concerned for better detection performance as well as communication systems, and in biology also. Okay, so this is called a wave shaping circuits. So from these terms we come to know about some of the applications of wave shaping circuits. Okay, so the wave shaping circuits is nothing but a smooth eliminate DC. Okay, that is smooth means low pass eliminate DC, high pass frequency selectivity, band pass interference removal, that is a notch. Okay, then it is used in an integrator and a differentiator, that is in a electronic, that is in a LIC and analog circuits. The ICs are majorly used for integrator and differentiator functions also. So those functions are performed by wave shaping circuits only. Okay, that is seeing that is we are seeing here. Then wave modification, so wherever we need some wave modifications to give input or some other processing, we use wave shaping circuits. Okay, next adjusting DC levels, clipping and clamping, pulse timings, that is a multivibrators. So these circuits are mainly used in practical applications such as radar, television, telecommunication, and computers. Okay, so these are the functions of wave shaping circuits. Okay, so next one is a triple five timer. Okay, so triple five timer. So this triple five timer is an integrated circuit. Okay, so this is a integrated circuit used in wide variety of timer, that is a delay, pulse generation, oscillator applications also. Okay, So it is an integrated wide array of pulse generation oscillators applications. So derivatives provide two, that is 556 and 558 timing circuits in one package. Okay, so it is mainly commercialized in Signetics by Signetics in 1972, and it was reported to still be in wide use of 2013. Okay, so numerous companies have made the original bipolar timers and similar low power CMOS timers too. In 2017, it was said over an billion triple five timers are produced annually by some estimates, and probably the most popular integrated circuit ever made. Okay, can you get this point? So I repeat once again, numerous companies have made the original bipolar timers and similar low pass sorry low power CMOS timers too. In 2017, it was said to be a billion triple five timers are produced. Okay, produced by some estimates. Okay, some estimates in the market, in the electronics market. Okay, so that is thing we said in this. Okay, so the some of the reasons, that is why it is called as a triple five. Okay, so those kind of things may arise in this time. Okay, so the basic triple five timer get its name from the fact that there are three internally collected 5 kilo ohm resistors, which it uses to generate the two comparators reference voltages. Okay, so that is the main reason behind the name. Okay, the basic triple five timer gets its name from the fact that there are three internally connected 5 kilo ohm resistors, which it uses to generate the two comparators reference voltages. The triple five timer IC is very cheap, popular, and useful precision timing device, which can act as either a simple timer to generate single pulses or long time delays, or a relaxation oscillator producing a string of stabilized waveforms of varying duty cycles from 50 to 100 percentage. Okay, the triple five timer chip is extremely robust and stable 8-pin device that can be operated either as a very accurate monostable, bistable, or a stable multivibrator to produce a variety of applications such as one shot or delay timers, pulse generation, LED and lamp flashers, alarms and tone generation, logic clocks, frequency division, power supplies and converters, etc. Okay, so these are the things we just seen. So the applications of triple five. Okay, so triple five, so pulse generation, LED and lamp flashers, alarms and tone generation, logic clocks, frequency division, power supplies and converters, etc. Okay, in fact any circuit that requires some form of time control, as the list is endless. Okay, so that is the main thing about the this triple five timer. Okay, the applications includes timers, missing pulse detection. So wherever I need some timing control, we will use this triple five timer. Okay, so this plays a major role. Okay, so includes that is a touch switches, frequency divider, capacity measurements, then bistable, that is flip flop mode. Triple five operates as a SR flip flops. Use include bounce free latch switches in PWM. The triple five timer is generally used. Okay, okay, right. So let us see some of the problems with the solutions that belongs to these operational amplifiers and function generators, wave shaping circuits, and voltage reference circuits also. Okay, so before that, let us see that what is maybe voltage reference circuit also. Okay, so voltage reference circuit is nothing but an electronic device that ideally produces a fixed voltage irrespective of loading on the device, power supply variations, temperature changes, and passage of time. Okay, can you get it? So a voltage reference is an electronic device that ideally produces a voltage irrespective of the loading on the device, power supply variations, temperature changes, and the passage of time. Okay, the voltage reference are used in power supplies, analog to digital converters, digital to analog converters, and other measurements and control systems. Voltage reference vary widely in performance. A regulator for a computer power supply may only hold its value to within a few percent of nominal value, whereas laboratory voltage standards have precision and stability measured in parts per million. Okay, I repeat once again, voltage reference are used in power supplies, analog to digital converters, digital to analog converters, and other measurement and control systems. Voltage reference vary widely in performance. A regulator for a computer power supply may only hold its values to within a few percent of nominal value, whereas laboratory voltage standards have precisions and stability measured in parts per million. Okay, okay, right. So let us see some of the problems which is related to the operation amplifier, function generators, and so on. Okay, so first, the expression for output voltage of non-inverting summing amplifier with 5 input voltage. Okay, option A, V naught, that is output voltage V naught equal to 5 into VA plus VB plus VC plus VD plus VE. Then option B, V naught equal to 1 plus RF by R1 into VA plus VA plus VB plus VC plus VD plus VE. Option C, V naught equal to VA plus VB plus VC plus VD plus VE. Then option D, V naught equal to the same thing, VA plus VB plus VC plus VD plus VE divided by 5. Okay, so the exact what is the sum? The expression for output voltage of non-inverting summing amplifier with 5 input voltages. Okay, so we have to calculate the output voltage for non-inverting summing amplifier with 5 input voltages. Okay, so based on the theory and the principles of operational amplifier, the output voltage of an non-inverting summing amplifier is 1 plus RF by R1. Okay, so that is a free feedback resistance, that is RF. So 1 plus RF by R1 times the average of all input voltage in the circuit. Okay, I repeat once again, the output voltage of non-inverting summing amplifier is 1 plus RF by R1 times the average of all input voltage is in the circuit. Okay, so in this problem, we are using 5 input voltages. So 5 input voltages, that is 1 plus RF by R1 equal to 5. Okay, therefore V naught equal to 5 into VA plus VB plus VC plus VD plus VE divided by 5. So that 5 cancels. So the output voltage we get equal to V naught equal to VA plus VB plus VC plus VD plus VE. Okay, so the option is C, option C. So V naught output voltage equal to VA plus VB plus VC plus VD plus VE. Okay, so this is the some model problems which are frequently asked in gate examination regarding this operational amplifier topic. Okay, so that's why we just seen what are the basics of operational amplifier and its applications. Now we are seeing the problems, solved problems. Okay, so the next one, find the value of V1 in the circuit. Okay, shown below. Okay, so in this there is a input. Okay, so it is given in the positive terminal. So what it is? So it is the inputs which are giving in a positive terminal is called non-inverting mode, and giving in a negative means it is a inverting mode. So it is given in a non-inverting mode. Okay, so the four inputs, so four input voltages, what are they? Plus 4 voltages, minus 3 voltage, plus 6 voltage, minus 1 voltage. Okay, all are connected through a equivalent resistance, that is 1 kilo ohm. Okay, so in this 1 kilo ohm, the value of V1, we have to find out the V1 value, that is input value. Okay, V1 we have to calculate. So it is already it is connected in a operation amplifier, that is IC74, which is nothing but an operation amplifier. Okay, so in this, so what is the V1 in the circuit? Okay, so exact input voltage, what is the input voltage? So the options are A 4 volt, B 2 volt, C 3 volt, D none of the mentioned. Okay, so based on the operation amplifier principle, we can calculate the V1 easily. Okay, so using the superposition theorem. Okay, there is a four voltages are given with equivalent resistance. So using the superposition theorem, the voltage v1 at a non-inverting terminal, as I said already, no, the input which is connected to the positive terminal is non-inverting, which is connected to negative is called a inverting mode. Okay, so this is a non-inverting mode. So in this non-inverting mode, the v1, okay, so v1 equal to VA by 4 plus VB by 4 plus VC by 4 plus VD by 4. So we are taking that is 4, the value 4 commonly. So VA plus VB plus VC plus VD by 4. Okay. So 4 plus minus 3 plus 6 minus 1. Okay. Which are given in this circuit. 4 minus 3 plus 6 minus 1. Okay. So divided by 4. So this gives the value 1.5 voltage. Okay, so the answer for this problem is 1.5 volt. Okay, so this is the find the value of V1 in the circuit. So these kind of problems also discussed in a gate examinations. So these kind of problems can be practiced well. Okay, for easy clearance. Okay, for we will get a easy score in a gate examinations in a simple manner. Okay, it is very easy to solve also. Okay, so next one, in the circuit shown, okay, this is the same kind of circuit. Okay, but we will see. Okay, in the circuit shown, supply voltage is plus or minus 15 volt. Okay, okay, right. So VA equal to plus 3 volt, VB equal to minus 4 volt, VC equal to plus 5 volt. So R equal to R1 equal to 1 kilo ohm and RF equal to 2 kilo ohm. So 741 op amps as a equal to 2 into 10 to the power 5 and R1 equal to 10 kilo ohm. Determine the output voltage internal resistance of the circuit. So it is also in the non-inverting terminal which is connected VA, VB, VC. So they given the value VA equal to 3 volt, VB equal to minus 4, VC equal to plus 5 volt. Resistance equal to also 1 kilo ohm, which we already seen in the last problem also. So frequency, that is a feedback resistance RF equal to 2 kilo ohm. Okay, so operation amplifier has A. சரியா, A equal to 2 into 10 to the power 5 and R1 equal to 10 kilo ohm. Okay, so in this output voltage internal resistance of the circuit we have to determine. So the solution, which is very simple. Okay, the output voltage, that is v naught equal to 1 plus rf by r1. We already discussed in the problem and we came to know about this thing from the theory also. Okay, so v naught equal to 1 plus rf by r1 into va plus vb plus vc divided by 3. Okay, so equal to 1 plus 2 kilo ohm by 1 kilo ohm. The RF and R1 values already given in the problem into VA, VB, VC already known. Okay, so that is equal to 3 volt. Okay, so it is solved and it is 2.67. So which is approximately equal to 3 volt. Okay, fine. Next, internal resistance of the circuit. So we have to calculate or determine the internal resistance of the circuit. So RIF equal to RI into A into R1 plus divided by R1 plus RF. So 100 ohm into 2000. Seriya, sorry, 2 lakh into 1 kilo ohm divided by 1 kilo ohm plus 2 kilo ohm. Okay, so that is equal to 6.67 mega ohm. Okay, so that is 6.67 mega ohm. So the value, the answer is option A. V naught approximately equal to 3 volt and R internal frequency. Yes, that is internal resistance. Okay, output voltage and the internal resistance of the circuit is 6.67 mega ohm. Okay, can you clear? Okay, fine. We will discuss the next one. That is simple, which is a little bit different from those problems we already discussed. So find the differential amplifier configured as a subtractor from the given circuit. Okay, we have to find out the subtractor circuit. Okay, oh, that's it. So let us see the option A. That is input voltage is given in a plus positive terminal, so it is a non-inverting. Option B also in non-inverting, option C is also in a non-inverting, option D also in a non-inverting terminals. So each and every circuits, the voltage, the given voltage and feedback voltage, that is resistance value only varies. Okay, from this circuit, there is operation the differential amplifier. We have to find out the subtractor from the given circuit. Okay, so general, so the solution, Basic differential amplifier is used as a subtractor when all the external resistance are equal in value. Okay, so it is equal in value. So the output voltage v naught equal to minus r by r into va minus vb. So va equal to v naught equal to va minus vb. So that is, hence the circuit is called as a subtractor. Okay, so the subtractor, which one is a subtractor, means the resistance value will be a equivalent value. So those circuit is the subtractor. Okay, so next one, this also very simple problem. So these kind of problems can be solved very easily and very much low time in gate examination. So keep it in mind. Okay, so let us see the calculate the output voltage for a summing amplifier given below, where R equal to 2 kilo ohm and RL equal to 10 kilo ohm. Okay, so the circuit is given. So in this 4 voltage VA, VB, VC, VD have been given, which is minus 3 volt, minus 4 volt, 6 volt, and 5 volt. So we have to calculate the output voltage for this summing amplifier. Okay, so the option given are option A 4 volt, option B 18 volt, option C 8 volt, and D none of the mentioned. Okay, so the answer, output voltage for summing amplifier is given. Okay, so we already know the summing amplifier. So v naught equal to, that is output voltage, v naught equal to minus va minus vb plus vc plus vd. So equal to 3 minus 4 plus 6 plus 5. So this gives 4 volt. So the answer is option A. Okay, so this is a very simple problem. So these kind of problems have been asked in a gate frequently. So which is easy to answer, but we have to know the principle and what are the techniques used in a summing amplifier, differential amplifier, and its definitions. Okay, so let us see the next problem. The output voltage of the summing amplifier is equal to, okay, so how the summing amplifier will looks. Okay, so option A, non-inverting terminal vn plus vn, so that is non-inverting terminal plus inverting terminal. Option B, non-inverting terminal minus vn, that is inverting terminal. Next, option C, non-inverting terminal plus inverting terminal, that is minus vn. Option D, minus vn non-inverting terminal plus vn inverting terminal. Okay, the output voltage of summing amplifier is equal to sum of the input voltage applied to the non-inverting terminal plus the negative sum of the input voltage applied to the inverting terminal. So this is a solution. So the output voltage of the summing amplifier is equal to the sum of input voltage applied to the non-inverting terminal plus the negative sum of the input applied to the inverting terminal. So from this explanation we will get the answer, that is option B is the right answer. Okay, vn non-inverting terminal plus negative sum of the input voltage applied to the inverting terminal. Okay, okay, let's go for the next problem. From the circuit, determine the output voltage. Assume alpha f equal to 1. So this there is a two transistors here. So it is called as a differential amplifier also. Okay. So option A, V naught 1 is that is a V1 3.9 volt, V2 12 volt. Option B, V1 12 volt, V2 3.9 volt. Option C, V1 12 volt, V2 0 volt. Option D, V1 3.9 volt, V not 2, that is minus 3.9 volt. Okay, so in this from this figure, the common emitter E will be minus 0.7 volt, which make Q1 off and the entire current will flow through Q2. Okay, can you clear? Okay, so the V1 equal to VCC into V02, that is equal to VCC minus alpha F into IQ into RC. So the V01 equal to, which we already know, that is a 12 volt. So V02 equal to 12 volt, that is VCC is 12 volt minus alpha F, the value which is already given 1, into 3 milliamps. Okay, 3 milliamps, which is already given, IQ equal to 3 milliamps. So into 2.7k. Okay, that is RC equal to 2.7k. So equal to 3.9 volt. Okay, so the answer is 3.9 volt. Okay, so V not 1 equal to 3.9 volt. Okay, okay, fine. So the next problem, find collector current So these are all the internal circuits of an operational amplifier, so which is discussing here. So some problems related to some depth manner. Okay, so find collector current IC2 given input voltages are V1 equal to 2.07 and V2 equal to 2.06 and total current IQ equal to 2.4 milliamps. Assume alpha equal to 1. So this is the question. So option A 0.8 milliamps, option B 1.6 milliamps, option C 0.08 milliamps, option D 0.16 milliamps. Okay, so let us see the solution part. So collector current, so IC2 equal to alpha f into IQ is divided by 1 plus e power v, that is divided by Vt. Okay, Vd by Vt, e power Vd by Vt. So Vt volts equivalent of temperature, that is 25 millivolt. Okay, which is given in the question. So Vd equal to V1 minus V2. So those values also given in the question. So let us form an equation, then we will get an solution very easily. Okay, so Vd equal to V1 minus V2. So 2.078 volt minus 2.06. So which gives 0.018 volt. So let us form equation as a 1. Next, substituting equation 1 in that collector current formula, that is Vd by Vt equal to 0.018 volt by 25 millivolt. So that is 0.72 volt. That is named as equation 2. Okay, so now we got equation 1 and equation 2. So let us solve very easily from those equations. Okay, so IC2 equal to alpha f into IQ divided by 1 plus e power Vd by Vt. So 1 into 2 power 4 milliamps. Okay, so the point 0.72, that is e power 0.72, which already given solved from the equation 2. Okay, so 2.4 milliamps by 1 plus 2.05, that is equal to 0.8 milliamps. Okay, so from the solution we got an answer 0.8 milliamps. So the option A is the correct one. Okay, so that is 0.8 milliamps. Okay, right. Let us go for the next problem. A differential amplifier has a transistor with beta naught equal to 100 is biased at ICQ equal to 0.48 milliamps. Determine the value of CMRR and ACM if RE equal to 7.89 kilo ohm and RC equal to 5 kilo ohm. Okay, so the option A is 49.54, option B 49.65, 49.77, and the final option D 49.60 dB. Okay, so we go for a solution. The differential mode gain ADM equal to minus GM RC and common mode gain ACM equal to minus GM RC divided by 1 plus 2 GM RE. Okay, for beta naught greater than 1, substituting the values. Okay, we already know the values which are given all in the questions already. So we have to recall the formulas which we studied during the theory classes. That's it. Okay, so GM equal to ICQ divided by VT. So the value is 0.48 milliamps divided by 25 millivolt equal to 19.2 into 10 to the power minus 3 omega power minus 1. Okay, so ADM equal to minus GM into RC, so equal to minus 19.2 into 10 to the power minus 3. Okay, so that is ACM and AD, that is GM values can be solved. That is CMRR equal to minus 96 by minus 0.3158 equal to 303.976. So 20 log of 303.976 equal to 49.65 dB. Okay, so the option is option B 49.65 dB. Okay, okay, fine. Let us see the next problem. Unstable multivibrator. So these kind of is are function generators also. So a stable multivibrator operating at 150 hertz has a discharge time of 2.5 meter. Find the duty cycle of the circuit. Option A 50 percentage, option B 75, option C 95.9, option D 37.5. Okay, so the solution is the frequency is 150 hertz. Okay, given. Therefore, we know the time. We have to calculate the duty cycle. So time is required. So therefore T equal to 1 by F. So 1 by F, that is 1 by 150 equal to 6.67 milliseconds. Okay. So duty cycle. So what is the formula for duty cycle? D percentage equal to T low by T into 100 percentage. So we already know that T and T low. So T low means 2.5 milliseconds, which is given in a problem itself, divided by 6.67, which we solved from the frequency, given frequency, into 100 percentage. So equal to 37.5 percentage. So the option is D. So the option is 37.5, that is option D. Okay. Okay, so these kind of problems are a little bit different from the previous problems, and these are the problems asked gate sometimes. Okay, but it is not a omitted one, but it must be carefully studied for our gate examination. Okay, keep it in mind also. Okay, okay, thank you. So next problem. So determine the frequency and duty cycle of rectangular wave generator. So already we studied the what are the concepts behind the wave shaping circuits. Okay, so in this problem we are using the triple five timer. Okay, so triple five timer used, and the duty cycle of rectangular wave generator also studied. So in this the option A, frequency is 63.7 kilohertz, duty cycle is 50 percentage. So in this manner, 53.7, 55 percentage, 43.7, 50 percentage, 60 kilohertz and 55 percentage. So what is the option? So let us see the solution part. So frequency, that is 1.45 divided by RA plus RB into C. Okay, so all those things have been given in the circuit itself. So where Ra equal to 100 ohm plus 50 ohm, so 150 ohm, Rb equal to 100 plus 20, 120 ohm. So F equal to 1.45 divided by 150 plus 120 into 0.1 microfarad, which the values mostly given in the circuit itself. So we have to analyze and study the circuit clearly to solve the problem very easily. Okay, so every values were given in the circuit itself with a very clear manner. So we have to analyze the circuit and predict the formula which we have studied from the theory classes. Okay, so if we know this problem, that is a formula, we will solve in a very short time. Okay, so it will very useful for you in gate examinations, for those kind of problems which are frequently asked. Okay, so keep it in mind. So come to the problem. So F equal to 1.45 divided by 150 plus 120 into 0.1 microfarad. So it gives a frequency value 53.7 kilohertz. Okay, now let us go for the duty cycle. Okay, so from this frequency value, we will easily predict the answer. Option, that is option B, frequency equal to 53.7 kilohertz. Okay, so so maximum our consideration is over. Okay, our concern is over. So that is we got an answer, but we have to calculate the duty cycle also, because in some problems they will ask frequency alone, but in problems some duty cycle alone. So in this kind of questions, you may get a struggle while calculating the duty cycle. Okay, but in this problem the frequency and duty cycle is the same option, so we will easily predict the answer. But in gate point of view, we have to solve each and every parameter clearly. Okay, so that's why we going to the duty cycle. So duty cycle already we seen this kind of problems and solutions in already last problem. So RB by RA plus RB into 100 percentage. So 0.55 into 100 percentage equal to 55 percentage. Okay, so the option B. So from the first parameter itself, we found the option, but we have to study, know the calculation of duty cycle also. Okay, so in this gate examination, they won't ask this kind of questions sometimes. Okay, so we have to know those formulas very clearly. Okay, okay. So next one, determine the output frequency of the circuit. So in this circuit, we have to find the output frequency. Okay, so in this also the same triple five timer has been used. So option A 1450, option B 1333, 1871, 1700 hertz. Okay, so the solution is very simple. So we have to study the and analyze the circuit first very clearly. Then you will easily solve the problem. Okay, so which will be very helpful for you in the gate examinations. Okay, so output frequency of the frequency shift keying generator, that is the circuit is a frequency shift keying generator. So the option also the same formula which usually in already last two problems we discussed the same formula. So f equal to 1.45 into, that is divided by RA parallel RC plus 2 into RB into C. Okay, so by applying those values in this formula, so RA equal to RB equal to, so RC equal to, okay, so those values has been replaced here. So the final value 1.45 divided by 7.75 into 10 to the power minus 4. So it gives 1870.9, so which is approximately 1871 hertz. So the option C is the correct answer. So 1871 hertz. Okay, so these kind of problems are very simple, but you have to predict that, you have to assume and analyze the circuit, which is RA, which is RB, which is RC. So you have to know the circuit. Okay, if you know the circuit clearly, then the solution is solved in very short manner. Okay, okay, right. So the next problem, find the input and output resistance of the circuit shown. Specification 7 operation 741. So each and every option values has been given. So A, Ri, R0, Rf, R1, everything is given. Supply voltage also plus or minus 15 voltage. Okay. So option A, option B, option C has been given. So in this, so we know AF equal to 1 plus RF divided by R1. So RF and R1 has been given in the question itself. So it is 6.5. So B equal to 1 by AF equal to 0.154. So input resistance, that is RIF equal to R1 into 1 plus AB. So we know the every values. So, okay. So A values we know, B value also know. So 33 mega ohm, okay, into 1 plus 6.5 into 0.154, it gives 66 mega ohm. Okay, so the output resistance ROF equal to R naught by 1 plus AB. Okay, so this value gives approximately 30 ohms. Okay, so the value, that is answer is option A. So RIF equal to 66 mega ohm, or output, okay, equal to 30 ohm. So in this kind of problems, you have to know both how to calculate the input resistance and how to calculate the output resistance also. Okay, because in point of gate, they may ask input resistance alone or output resistance alone. So if they ask the questions like this, we may struggle at some time. So we have to exactly calculate the input resistance IF also and output resistance ROF also. Okay, we know these techniques. Otherwise, because if the questions are asked, this kind of questions sometimes asked, so we will easily predict by calculating the first value. Okay, but if they are asking the values alone, we know the formulas. Okay, so you have to know the kind of techniques which are used to solve in very short manner. So you have to know about the how to calculate the input resistance and how to calculate the output resistance, both the parameters also for a given circuit. Okay, so that is the main thing in gate examination. So many of the students are not concentrating on those kind of formulas, so they may fail, or some marks may reduce for their gate result. Okay, so that may be considered in your mind, and you have to know the all those formulas. Okay, okay. So next one, when the non-inverting input terminal of an op amp is equal to that of inverting terminal ideally. Okay, so the option A belongs to infinity, VID approximately 0, AF equal to 1 plus RF divided by R1, all of them mentioned. So when the input at both the terminals are equal, the difference input voltage VID equal to V in 1 minus V in 2. Okay, the open loop voltage gain A equal to V naught by VID, the closed loop voltage gain AF equal to V naught by V in equal to 1 plus RF by R1. So the option is C, AF equal to 1 plus RF divided by R1. Determine the lower cutoff frequency of the circuit. So next problem belongs to determine the lower cutoff frequency of the circuit. Okay, so this is a circuit, you have to study the circuit and you have to answer. Okay, the input resistance of the amplifier is RIF equal to R2 parallel to R3. Okay, R2 and R3 are parallel into Ri into 1 plus AB. So this is equation 1. So we have to solve by forming equations. So this kind of problems may take some more time. So you have to concentrate on the formulas very well. Then you will easily form those equations and easily get a solution. Okay. So lower cutoff frequency FL equal to 1 divided by 2 pi Ci input capacitance into RIF plus R0. So everything, every values has been solved here. So the final values, that is FL lower cutoff frequency equal to 6.75 hertz. Okay, that is 6.75 hertz. Okay, so the next problem. So next problem, linear ramp generator. RE, R1, R2, C, VCC, every values has been given here. So we have to, as usual, study the circuit and form the formula, then solve. Okay. So the ramp generator T equal to 2 by 3 into VCC into RE, R1 plus R2 into C divided by R1 into VCC minus VBE into R1 plus R2. This is the formula for ramp generator to calculate the time period. So every values has been given in the question itself. So RE given, R1 given, R2 given, C given, VCC, everyone, everything is given. So we have to calculate the, we have to determine the formula to solve this. Okay, so everything, every value is given. So applying the those values in the formula, so T equal to 132.3 divided by 132.100, so which gives 1 millisecond. So option D. Okay, so I am repeating once again, these kind of problems requires just in 3 steps. Okay, the first step, you have to analyze the circuit. Next step, recall the formula. Third step, you have to apply those values in the recalled formula. That's it. Okay, you have to follow these 3 steps to solve the problem in very short time, which will boost your gate score very easily. Okay, so determine the frequency and duty cycle of a rectangular wave generator. Okay, so this problem also we discussed earlier. Okay, so we already discussed the same method. Okay, so this one also. Okay, so next one, find the capacitor for value for our output frequency f naught equal to 2 kilohertz into, that is v naught pp equal to 7 volt. Okay, the operation amplifier 1458 by 741 and supply voltage is plus or minus 15 volt. Take internal resistor as 10 kilo ohm. Okay, for this given saturation value equal to 15 voltage, v naught equal to 2 r1 divided by r3 into v saturation. Okay, so again the same thing, predict, that is studying the circuit, recalling the formula, then applying those values in that formula. Okay, so the output frequency f naught equal to r3 divided by 4 into r1 into c1 into r2. Okay, that's it. So from this we know that that c1, that is a capacitance equal to, that is approximately equal to 3 nanofarad, that is option D. Okay, so these are the, these kind of problems may ask sometimes in a gate. So but you have to follow those 3 steps. Okay, so just follow the circuit, assume, that is see the circuit and study the circuit, then predict, that is interpreting the values, that is which is ra, which is r1, which is rb, then recall the formula, then applying those predicted, that is interpreted values in those formulas. Okay, so that's 3 main thing which you have to use to solve in a very simple manner. Okay, we very short time, we will use a very short time and we will solve that problems very easily. Okay, so this kind of problems frequently asked in gate examinations. So study these kind of problems and practice more worked out problems like this in analog circuits, related to analog circuits. Then you will get a better result in gate examinations. Okay, so all the best students for gate examinations. So please follow those slides carefully to answer and how to solve those kind of problems and practice more problems like this. Okay, then you will get a good score in gate examinations. Okay, okay, thank you, thank you for your patient listening. Okay, thank you.